Alright y'all, we're going to look at question 4 for Recitation 7, which is the uniform electric field, and we're finding the electric flux through a circular area of radius 2 meters that lies in the xy plane. So what we're going to do to start is, I'm just going to start with the easy part. The area of that circle is, I'm just going to use the variable a for that, and that's going to be just pi times our radius squared, which pi2 squared, 4 pi. That's just geometry, and that is my favorite part of this problem. Alright, so I just copied down the electric field vector for us to use later, because what we're going to do, we're going to be using the equation that our flux is equal to our electric field vector dot our A vector, because that's our field times the area that it's passing through, and that's going to give us our flux. That's just the definition. So now we're going to take a look at this A vector, right? So that what the A vector is going to be, that's going to be our n hat, which is our unit vector, giving us the direction normal to this area, times the magnitude of the area, and it's not dot or cross because we have a scalar and we have a vector, and that's going to give us another vector. All right, so we're going to have to find this normal vector, which is normal or perpendicular or orthogonal if you want to be real fancy about it. That's going to be perpendicular to this surface here. And in the problem, it says that our circle, it lies in the xy plane, right? So xy plane, we're trying to find something that's perpendicular to the xy plane. All right, so when we set up our axes, we're going to have x here, y here, and z here, just for the sake of simplicity. And then our xy plane is this up here. That it's going to be when z is equal to 0, right? So if we're looking for something perpendicular to this plane, it's going to be coming out kind of like that, and that's going to be our z vector, just in our z direction, right? Because that's what's going to be perfectly perpendicular to that. And our unit vector that's just straight down the z-axis, that's our k hat. So our k hat is actually going to be our n hat. So that's where we can then put that into this and plug that into that and get that our flux is equal to the electric field, which again we have here, dotted with this n hat vector, which is just our k hat. And that's going to be times the magnitude of the area. All right, so I just went ahead and plugged in each of our values now because we have this electric field vector given up here with these there, and then our area just plugged in there, multiplied by that k to give it the direction. So now I'm just going to dot them together. So we have this j value, and we have 0j over here, so it's going to be 4 times 10 to the third times 0, plus our k component here, 3 times 10 to the third, and that's times our k component here, and since it's all k component, it's just going to be 4 pi. And obviously we had 0 in the I direction for both of them, and that's equal to our flux. So now this is anything times 0, this is just going to go to 0, and this, when we multiply this out, that's going to give us our final answer, which when we do, it's our flux equals 3.769911184 times 10 to the fourth. And that's still, since we're doing flux, it's in newtons meters squared per coulomb. And that's going to give us our final answer. Well, if we round it, 3.76, we'll round to 3.8 times 10 to the fourth, and that's what we have for our answer up here. All right, and thank you all again so much for watching. Let me know if you have any more questions about this, or if you have another problem that you want to see worked out, and I will do my best to explain it, because I guess Sydney explains stuff.